Hi, I'm Manthan and I'll be presenting the paper, A Comparative Study of Different EMG Features for Acoustics to EMG Mapping. This is the outline of the presentation. First, I'll give a brief introduction about the work, then I'll go into the details of the study and talk about the experimental setup. I'll conclude my presentation with the results and discussions. Let's first start with the introduction. So what is EMG? Electromyography or EMG is a technique for evaluating and recording the electrical activity produced by muscles. In this work, the EMG signal captures muscle activities resulting from the articulatory muscle activations during the speech production. There are mainly two objectives of this work. First is to estimate the EMG signal from speech acoustics, which is essentially divided into two steps, that is speech acoustics to EMG inversion or Aei mapping as we call in this work, and then reconstructing raw EMG signal from the EMG features, which is step 2. To do this, we find the best EMG feature representation for the Aei mapping and raw EMG reconstruction. The EMG feature representations in this work are divided into three categories. So firstly, we examine the existing time domain features of the EMG signal. Secondly, we explore non-speech temporal features of the EMG signal. And lastly, we introduce a novel Hilbert transform based feature for the EMG signals. Few of the applications of this work. So it can be used to visualize the facial muscle activity from speech signal. This can also be helpful in identifying key muscles which are getting activated for each phoneme, which can further be useful in improving speech synthesis and recognition. The synthetic EMG signals generated from these mappings can also help in improving the EMG to speech acoustics forward mapping performances. It can be also helpful in solving the low resource problem of the EMG acoustic data. Now coming to the baseline work. So Botello et al. Used 5 TD features for the Aei mapping. They used a simple DNN-based network for the Aei mapping by using stacked input frames of the MFCC to account for the temporal dependencies in the data. And for the raw EMG reconstruction, they used a CNN BLSTM-based network to map from the TD features to the raw EMG. They achieved a concordance correlation coefficient value of 0.65 for the Aei mapping and 0.66 for the raw EMG reconstruction. Now coming to the data set which is used in this work. So the EMG UK corpus consists of parallel recordings of surface electromyography and acoustic recordings of speech in the English language. These have been recorded at KIT lab in Germany. The full corpus has two large sessions, recordings from two different subjects, that is UK1 and UK2 as we call in this work, with 520 and 509 utterances respectively. These two large sessions are used for the session dependent AEI mapping. And for the raw EMG reconstruction, we use the entire audible corpus from the EMG UK corpus. The audio sampling frequency is 16 kHz and the EMG sampling frequency is 600 Hz. The EMG signal in this work is 6-channeled, essentially targeting 6 prominent articulatory muscles like levator anguli oris, zygomaticus major, platysma, depressor anguli oris, anterior belly of the digastric, and tongue. Now coming into the details of the study. So there are three different EMG feature extraction methods broadly. So firstly, TD features. These EMG features exist in the literature and are associated to speech tasks, capturing the temporal variations of various short time features like low frequency power, low frequency mean, high frequency power, high frequency rectified mean, and high frequency zero crossing rate. Secondly, the NST features or the non-speech temporal features. These features exist in the literature when EMG is collected during a non-speech task. Some of them are mean absolute value, root mean square, de Villa's method, and low frequency bandpass. Lastly, we also introduce a Hilbert transform based feature. These feature captures the temporal envelope of the broadband EMG signal. Now getting into each feature extraction method in detail. So firstly, talking about the TD features. These were introduced by Zhou et al. In a work related to speech recognitions using the EMG signals. In this work, the TD features are extracted using a 25 millisecond window with a shift of 10 millisecond using a Blackman filter. A TD feature vector for a frame is represented as this. Let's now dive into the NST features or the non-speech temporal features, namely MAV, DAV, etc. So let the original EMG signal, which has been resampled to 1000 Hz and then bandpass filter between 3 to 300 Hz be represented as X of n. And let the square of that signal be represented as S of n. Since the signal is sampled at 1000 Hz, So for a window of 10 milliseconds, we represent it as W equals to 10. Starting with the mean absolute value feature, it is, as the name suggests, it is the mean of the absolute values of the signal in a window. It is commonly used for wrist and hand movements. Now coming to the root mean square feature. It is also, as the name suggests, so it is the mean of the square of the signal in a window and then taking the root over it. These features have been used for EMG signals while recording wrist and forearm motions. It has also been used for leg motions during cycling. Let's now talk about the third NST feature, that is the DAV feature. We first low pass filter the square of the signal with 20 Hz cutoff frequency to get U tilde n. We then take the mean of the absolute values of the U tilde n to get the DAV feature used in this work. Now coming to the LFB feature, we first bandpass filter the signal x of n from 5 to 15 Hz to get U hat of n. We then take the absolute value of the U hat of n to get the LFB feature used in this work. Now coming to the Hilbert feature. So Hilbert transform based feature of the EMG have been popularly used in past, like Hilbert-Wang transform of EMG signals for speech recognition and iterative Hilbert transform for the upper limb movement in humans. In this work, we use the Hilbert transform to develop a novel feature extraction method for the EMG. So let's say the Hilbert transform of the signal x of n be represented as xh of n, and together with the x of n, it represents a complex analytic signal xa of n. Here the real part consists of the original data and the imaginary part consists of the Hilbert transform of the signal. This analytic signal can be represented in the magnitude phase form as a of n e to the power j phi n. We then take the absolute of this analytic signal to get a of n, and we finally apply a low pass filter with cutoff frequency of 20 Hz to get the Hilbert feature as we use in this work. These are the plots of different EMG features which are time aligned with the original EMG signal. Here green label represents the NST features and the red label represents the time domain features, whereas the unlabeled is the Hilbert feature. Now coming to the model architectures. So firstly talking about the Aei mapping model architecture. The network has 5 BLSTM layers with 128 neurons in each layer, followed by a time distributed fully connected output layer. The tan activation function is used for all the BLSTM layers with a dropout probability of 0.2. Mean squared error and concordance correlation coefficient based laws introduced by Botelho et al. Are separately used as objective functions with the Adam optimizer to update the model parameters. Here the mean squared error loss was found to be performing better than the CCC based loss. The output layer here has linear activation function. Now coming to the model architecture of the Raw Emg Reconstruction. It is a CNN BLSTM based network. In this, the information from the TD features is extracted using a 3 CNN layers followed by 3 BLSTM layers. And the information from the Hilbert feature is extracted using a BLSTM layer, which are then concatenated in a later stage in network and passed on to a BLSTM layer, which then maps it to the 6-dimensional Raw EMG vectors. Now coming to the experimental setup for the Aei mapping and the Raw EMG reconstruction. So firstly talking about the experimental setup of the Aei mapping. 25-dimensional MFCCs are used as speech features which are extracted by using a 25 millisecond window and a shift of 10 milliseconds. The output to this model is the EMG feature matrix of the form T cross C, where T is the number of frames in an utterance and C is the number of EMG channels. The input to this model is the corresponding sequences of the MFCC vectors. We do a session-based training for 50 epochs with an early stopping criteria to avoid the overfitting. We do a 10-fold cross-validation, and the prediction performance of the Aei mapping model is measured using the correlation coefficient. Now coming to the Raw EMG reconstruction experimental setup. The input to this model is the EMG feature matrix TD plus Hilbert, where T cross F is the matrix for the TD feature and the T cross 1 is for the Hilbert feature, where T is the number of frames in an utterance and F is the number of TD features used. Non-overlapping windows of 10 milliseconds on the raw EMG signal gives us the 6-dimensional output vectors to this model. We use two different TD feature configurations in this work. First is the LFM, LFP, HFP, HFZCR and HFRM, and the second configuration is excluding the HFZCR. We do a session independent training in this case, and we then do a tenfold cross validation. The performance of the Raw Emg reconstruction model is also measured using the correlation coefficient. Now coming to the results and discussions. So these are the results of the Aei mapping. The table here mentions the CC with the standard deviation in the brackets for both the subjects UK1 and UK2. The left hand side of the table mentions all the TD features and the right hand side mentions the NST features and the Hilbert feature. Coming to the key observations which can be drawn from this results of the Aei mapping. So Hilbert based feature performs better than all the other feature extraction methods. The DAV feature performs the best amongst the NST features, that is MAV, RMS, DAV and LFB. The subject UK2 is found to be performing better for all the other feature extraction methods than the subject UK1, which essentially shows the session dependent quality of the Aei mapping. These are the illustrations for the Aei mapping. The plot with the red label shows a TD feature and one with the green label shows a NST feature. The unlabeled plot is for the Hilbert based feature. It can be seen that for the same utterance, Hilbert feature is being mapped with higher correlation value than the other two features. These are the results for raw EMG reconstruction with different EMG feature configurations. Table here mentions the CC values where mean is taken across all folds. It can be seen that the introduction of Hilbert feature along with the TD features significantly improved the CC value for both the TD feature configurations. Now these are the illustrations for the raw EMG reconstruction. The first plot shows the TD to raw EMG reconstruction and the second shows the TD plus Hilbert to raw EMG reconstruction. It can be seen that the introduction of Hilbert feature is leading to improvement of the correlation value from 0.54 to 0.73. Now coming to the conclusion. So few of the key points in this work. Aei mapping shows a session dependent characteristic as the subject UK2 is found to be performing better than the subject UK1 for almost all the feature extraction methods. We introduced a novel Hilbert feature which performs the best for the Aei mapping, and these Hilbert feature also helps in the raw EMG reconstruction more efficiently rather than just using the TD features. The TD feature configurations used in this work are divided into two steps. One is including HFZCR and second is excluding HFZCR. So the TD feature configuration including HFZCR is found to be performing better for the raw EMG reconstruction. Now in the end, some interesting extensions to this work. So we'd like to reconstruct raw EMG signal using the predicted features from the Aei models instead of the original EMG features as we use in this work. Would also like to develop custom objective functions to train these models. The methods to obtain intermediate learnable representations of the EMG signals for the Aei mapping is an interesting extension. Subband features of the EMG signals can be explored because they can potentially capture the intricacies of these complex EMG signals better than the full band as we use in this work. We want to develop session independent models so that the applicability of these mappings can be translated into real life settings also. The authors thank the Pratiksha Trust for their support in this work. Thank you. If you have any questions or suggestions, write to us at spirelab.ee@isc.ac.in. Thank you.